I made a trip down to the National Weather Center to meet with Don Burgess, who explained to me what we learned from the Vortex 2 project.
All right. My name is Don Burgess. I'm a research scientist here at the National Severe Storms Laboratory. I'm actually retired from the Severe Storms Lab, and I work for the University of Oklahoma. We have a cooperative institute with the lab, so I work for OU and work back with the folks that I worked with before I retired. So I was a part of Vortex 2. Vortex 2 stands for Verification of the Origin of Rotation in Tornadoes Experiment. Turns out to be Vortex. And 2, this is the second phase, the second time we've done this. We did it back in the mid-90s, and then we had a second experiment that we just completed in 2009 and 2010. Our 2009-2010 experience is the largest mobile field program that's ever occurred to try and study tornadoes.
Don, I understand you were one of the pioneers of Doppler radar. Can you give me a little history of the development of Doppler radar and your involvement in that development?
Turns out I began my career at the National Severe Storms Laboratory in 1970, 42 years ago now, and I was lucky enough to join the Doppler radar program as it was first developing. So we had a first radar that was actually government surplus, a warning radar that had been used on the DEW line for national security, and we got that for the non-military part of government use and developed it in the 1970s, and we learned that Doppler radar could really help warnings and weather forecasts. Doppler radar is like any other radar. It sends out a beam of electromagnetic radiation. That radiation bounces off of, in our case, precipitation particles. In the military case, they were looking for airplanes or rockets, but we configured the radar to look for precipitation particles. Part of the signal returns back to the radar. The amplitude of that signal tells you the reflectivity, how heavy the rain is, the possibility of hail. But we also can measure the motion of those particles with a Doppler shift, and that's why it's a Doppler radar. So we can see the rotation or any other kind of wind field up in the cloud. And seeing rotation then is very important in having precursors to tornadoes. So Doppler radar is very important in a lot of areas of weather forecasting and weather warnings, but particularly tornado warnings.
Don, can you tell me a little bit about Doppler on wheels and how that started?
We started maybe 40 years ago with radars that were fixed base units. And we've developed those, and we have a new network, or what was new in the 1990s, a new network of Doppler radars. And our newest thing is to have mobile Doppler radars. And the first version was called Doppler on Wheels, the first unit that was built. And our partner in that work was Dr. Josh Werman, who's now works out of Boulder, Colorado, the National Center for Atmospheric Research. But for a time, he was at the University of Oklahoma. And he built the Doppler on Wheels, and we worked together to use that radar. And having a mobile radar, we can get up very close to the storm and get very high resolution information. For instance, if you want to know the wind speed in the tornado, you need to be up very close to the tornado to get high enough resolution data to measure maximum wind speed. Since the Doppler on Wheels, we've gone on to develop a number of other mobile radars, and now here at the laboratory and with our OU partners, I think we have 6 mobile radars that we're using.
Yeah, is there a difference in the type of mobile radars that you use?
Well, there are differences. There have been improvements over time from the first ones we developed back in the 1990s. Our most modern radars have much bigger and fancier processing capability. Of course, computers have gotten better in the last decade. We get new kinds of data. We can send out signals that are polarized horizontally and polarized vertically. And by looking at the 2 different polarizations, what they call dual polarization radar, we can get information on the size, shape, and distribution of the precipitation particles. So that's an important addition. We also have radars whose antenna can rotate very fast, rapid scanning radars. And that's important to not only get the data, but to get it quickly. We might be able to revisit the same point in space every few seconds instead of maybe once a minute. So as something like a tornado evolves and evolves quickly, then we can better follow that with a radar that has a rapid rotation of its antenna.
I understand one of the discoveries that came out of Vortex 2 was this interesting little band that showed up on radar that kind of had a little curve signature to it. Can you tell me about the discovery of that and what that means?
Well, we're learning lots of things. We had a list of objectives for Vortex 2, and we collected data on those objectives, and we're making progress. I think what you're asking about is something new that we've seen, and we're not even yet completely sure what it is. And that's something we call a low reflectivity ribbon. And it's an area of weaker reflectivity between the forward flank and the rear flank of the storm. It doesn't occur with all storms. It doesn't even occur with all tornadic storms, but we've now seen it in several of our tornadic storm cases. We're not sure what it is or what role it plays, but it's something we're going to investigate further.
Wow, that's interesting. I understand Vortex 1 and 2 were tremendously successful and you learned a lot. Now, are there plans for Vortex 3?
We're getting ready to start that planning. We have a meeting next spring where we're going to go over what progress we made in Vortex 2, what new things we've seen, what new hypotheses we might need to generate for things like the low reflectivity ribbon, and when we might go to the field again. Now, this kind of research doesn't occur as a big program every year. As a matter of fact, it's maybe once a decade, but it takes several years in planning. So we'll probably start planning next year, 2013, but it may be 2015, 2018, or even 2020 before we go to the field again. So there will be a lot of work and maybe some small experiments to get ready to do another big field experiment.
Awesome. Now, one of the things as a native Oklahoman, because it was so powerful, and I understand the wind speed was off the charts, it was over 300 miles an hour, was the May 3rd, 1999 tornado. Was there really anything significant or anything that really sticks out about that event that you can tell me?
Well, that was a very powerful tornado. And with the Doppler on wheels, the first of our mobile radars, we made a measurement of wind speeds of 318 miles per hour. So the strongest winds that have ever been measured in a tornado has not been superseded since that time. But we have seen other very strong tornadoes with wind speeds almost that strong, including the tornado that struck El Reno in Piedmont last spring on May 24th, had wind speeds not quite 300 miles per hour. So it was also a very strong tornado. We collect data on all number of tornadoes, though. And some big tornadoes can do lots of damage, yet not have wind speeds as powerful as those two I just mentioned. For instance, on May 3rd, there was a tornado up at Mulhall that was very big and very damaging, but it stayed mostly in a rural area, struck only a part of Mulhall. Other storms that we've collected data on in Vortex 2 didn't strike anything, yet they were very powerful tornadoes. So, although we've made these measurements in Oklahoma, very powerful tornadoes, there probably are other tornadoes that are maybe equally as strong. We just haven't been able to make those measurements.
Did that May 1999 tornado, did that set the wind speed record for the planet as the fastest wind speed ever?
Yes, it's the fastest wind speed that's ever been measured either directly or indirectly at the ground in a storm. That is the high wind speed record.
I was always intrigued by that. I had a friend of mine that was living in Guam, and there was a super hurricane that went through there that had some wind speeds close to 300 miles an hour. He was just telling me it was scared the living daylights out of him. And a lot of people don't realize how powerful that storm was, and that something like that happened right here in the U.S. in the heartland.
That's right. Hurricanes and tornadoes both have very high winds. But I think we've learned over time that tornado wind speeds are just a little bit stronger than hurricane wind speeds for the strongest that do occur. And for these very high wind speeds in tornadoes, fortunately, they don't occur very often.
I also understand that you have some other instruments that you use, something called stick nets and mesonets. Can you explain a little more about that?
In Vortex 2, and some other experiments as well, we use several types of instruments. Of course, we've talked about radar, and radar is very important. but we need measurements of the temperature and the dew point and the wind right on the ground. So we have mobile measurements, which are vehicles with instrument packages on the top of the vehicle. Data, we use all of these mobile mesonettes, and in Vortex 2 we used even more. We had 10 mobile mesonettes during Vortex 2. They have instrument packages on top. They measure temperature, moisture, pressure, and wind, and they are calibrated to collect this data while the vehicle's moving down the road, so they can subtract out the movement of the vehicle, and they're used to collect data following the roads and highways underneath the storm. And because they're underneath the storm, they are susceptible to getting hit by hail. You can see the dents on the hood of this vehicle where it was hit by hail. And here it was hit on the windshield, and it cracked the windshield. This windshield has not been replaced. When we're out in a big experiment like Vortex 2, we lose lots of windshields. We provided money to replace 50 windshields during Vortex 2, and we ended up spending all that money. We replaced over 50 windshields. This is really a field control center. It has a satellite dish you can see up on top, and it has a tall antenna that's telescoped down now but raises to 150 feet above the ground. And so it's very good for communication, has a number of computers inside. So we can gather information from satellites and from radio and take that information and transmit it to all these other field vehicles and radars. So this is a very important vehicle for Vortex 2. For a project like Vortex 2 that's very large, it's beyond the scope of any one government laboratory or any one university. So we band together to do something like Vortex 2. And the funding comes from the National Science Foundation for the universities and from the federal government, from NOAA, National Oceanic and Atmospheric Administration, which is the parent of the National Weather Service and parent of the National Severe Storms Laboratory, provides funding to go along with the funding for the universities. And we write a joint experiment proposal. We get the funding from those two agencies, and then we work together to carry out the experiment. An experiment like Vortex 2 has over 50 vehicles and 150 people. So it's a mixture of federal employees, university students and professors, and we all work together. Here at the University of Oklahoma, we have the fortunate opportunity to be in the same building as the university. We can work with the graduate students. We can be on their committees, even though we're government employees, and we can all work together in the research.